every node that I have should be part of a segment tree. This is going to be a segment tree. This is going to be a segment tree here.
Trees? Everywhere trees? What the hell is this place?
This video is primarily possible because of Amandeep, who's a software engineer at Uber. He's been instrumental in explaining everything when it comes to the algorithm, when it comes to the implementation. If you're looking for code for the implementation, I have the link in the description below, again written by Amandeep. Also thanks to Anudeep Nikanti, who has written a blog on this, I think around 5 years ago.
It's a complicated topic, so I'll try to break it down into simpler parts. First, we'll talk about the problem statement, which will give us a use case for heavy light decomposition. At the end of the video, we'll actually solve a problem from Spoj, which is based on heavy light decomposition. We are given a tree which is rooted at Z, and we need to answer two types of queries efficiently. The first one is to find the sum of all nodes between two given nodes. And the second type of query is to update a given node. And these are the constraints of the problem. The brute force approach to solve this problem requires a couple of depth first search. You first go to node A using a DFS, and from A you start searching for B. When you get to B, you count the sum of all nodes in that path. Now this is going to take you order n per query for sums. And in the worst case, if there are q queries, this can be order qn, which is a huge amount of time and will not pass the time limit. A much better approach is to find the lowest common ancestor of A and B. Now if you do this on every query, that's a problem. That's going to take a lot of time, which will be a depth first search. So instead, if you can pre-compute certain values, which is ancestors of A and B using the technique of binary lifting, you can find the LCA of A and B in log n time. Once you have the LCA, you move from A towards Z and B towards Z, take the sum of all nodes, and you have the answer. What's the time requirement here? To find the LCA takes log n time, and to move from A to Z can take order n time. Similarly for B, Q queries, it's still order Qn. We'll look at how we can improve this. The other thing to keep in mind is that any node can have its value changed using the second type of query. So the node with value r can suddenly have a value of n, and that completely changes the answers that we could have pre-computed previously. So what we are looking for is a data structure which can handle both queries and updates on ranges.
What if we had this chain, these three nodes as one segment tree, being represented by one segment tree which can allow updates and range queries in them? Similarly, a segment tree which represents Z, P, J, R and B. I'm going to treat this path as an array. I can now make a segment tree out of this. Every node that I have should be part of a segment tree. This is going to be a segment tree. This is going to be a segment tree here. If you had more nodes here, then this would also be a segment tree.
I'm hitching a ride back home.
We have taken this tree, we have broken it into pieces, which will allow us to perform range operations on a tree efficiently.
For now, let us assume that we have already broken this tree into chains. That is, the heavy light decomposition of this tree is already completed, and we are more concerned about answering queries on this tree.
Given two nodes, A and B, how do you jump from one segment to another? We talked about finding the lowest common ancestor. The lowest common ancestor between A and B is the root. So this is the LCA. From A, I need to get to the LCA. How? Well, I could go from A to its parent and then to its parent and then to its parent, but this is very slow. It wouldn't actually make sense to break into trees then. The reason we have this chain given to us, we have this segment given to us, is because it's backed by a segment tree. So finding the range of all nodes from A to this point X is a very fast log n operation. In log n time, you can find sum of all nodes from A to X. Then all you need to do is move from X to its parent. And how can I be very sure when I'm moving from X to its parent that I'm not actually losing track of B? Well, because I'm always, whenever I'm heading up, I'm heading towards my LCA. There is no chance, when I've broken it into segments, that I'm not heading towards my LCA. I mean, I'm not breaking the chains like this. This is illegal for me. I have linear chains which head downwards. They never head both ways. Now think about B. B is just one node. So first it finds the sum of all nodes from B to B. Yeah, because it's the start. Then it heads to its parent. From its parent, I need to go upwards. How much upwards? All the way. because I know that this chain is not belonging to the same chain as the LCA. So I go up, let's call this node X, the sum of all nodes from X to X. Now I head to the parent, and at the parent I see that this node has the same chain as the LCA. I'm going to use the segment tree to answer this query, which is the sum of all nodes from this node, let's say Z. This gives me an answer. And jumping to a parent is an order 1 operation. Getting the segment tree queries is log n. Similarly over here, similarly over here. If you have a look at all of these operations, what we are effectively trying to do is move to the same chain as the LCA. Once you're on the same chain as the LCA, the segment tree for the LCA chain can answer your query efficiently. If you get to this point, you're on the same chain as the LCA, you need one query which is going to answer the range query over here. If you get to this point, the segment tree will take care of it. So your main goal is to get to the chain where the LCA belongs. How does A get there? At every point, what A needs to do is head to its first node, its topmost node in the segment tree as quickly as possible. That's the main logic.
Let's do some time complexity analysis. The update operation doesn't change the structure of the tree, just the value. So the ancestors don't change. But because of the change in value, you need to go to the segment tree that this node belongs to, the chain that this node belongs to, and update all the values in that tree, which is going to be a log n operation. And for querying, we are moving from a given node to its start node, jumping up the chain, and then again moving to its start node of that chain, and then jumping up the chain, so on and so forth, till we hit the chain of the LCA node. So every query from a given node to the start of its chain is going to be log n time, and every movement up the chain is going to be order 1, but we are doing this multiple times, so the total time complexity is log n into the number of chains we have to jump, which is the maximum number of chains we can have in a given path. If we can reduce this factor, then we'll have efficient querying. What we are now going to do is build this tree in a way that CP is reduced as much as possible. Let's see how.
What we need for this is some simple depth first search to be done on the tree first. So firstly, what are we going to do? We are going to be finding all the subtree sizes in this tree. Depth first search, you come here, you go here. There's a leaf node, the subtree size is 1. Similarly, you come back here, you go here, and first come over here, subtree size is 1. You update this to have 1 plus 1 plus 1, which is 3. Over here you have 3 plus 1, which is 5. Here we can apply our greedy strategy. You start off with just one chain, just one segment, which is the root node. You're either moving to the left or to the right. Which one do you choose? Logically, you choose the one with the maximum number of nodes as its subtree. So you head over here. From this point, you get just one subtree, which is 5. From this point, again, you choose the largest subtree, which is 3. And finally, you come to any one of these, but I'll just choose this one to get this entire chain. This has to form a separate chain now because it can't be part of this chain. As you know, you can only head to the left or right. You can't go to both directions. So 5 and 4 are compulsorily together. But over here, you can choose any one of these 3. Choose the leftmost one, and you have this separate chain over here. And over here, you can see that these are chains in themselves, giving us the heavy light decomposition for this tree.
So from the original tree, every node now has a heavy path which is taking the maximum amount of load. Because of this heavy path, what we are trying to do is attach as many nodes as we can to a single segment tree. The reason for that is that a segment tree gives us very fast query times, log n time. You don't want to be jumping the paths much. You want to attach as many nodes as you can to a single segment tree so that you can run along that as quickly as possible in most cases. Let's see exactly how that helps us.
We are mainly interested in the time complexity, which is log n into the number of chains you have in the path from A to B. The number of chains is defined this way. You come to the root. If you choose a heavy edge, you're actually continuing down the chain. So you haven't changed anything. If you go to a light edge, you changed your chain. So you have to do log n more operations for that particular chain. But how many times does that happen? Well, the first time you had your search space being the size n, total number of nodes. I mean, at the root, you're looking at everybody. You can move to just one node. So you move to a light node, you lost your heaviest and all other nodes which are light, which means that you lost n minus nodes in your path. In the worst case, the node that you move to, the chain that you move to, did not lose many nodes. This is the worst case. N is positive, minus nodes path is negative. So you want to effectively maximize the number of nodes in your path. Of course, this makes sense because you go to a place which has a lot of nodes. That is the worst case. The number of nodes you have in your path is less than the number of nodes that the heavy edge had in its path. Even if I make this equal to this node's size, that still gives me total number of nodes in path is less than or equal to the sum of nodes you had in this subtree, which is n by 2. If you get rid of half the number of nodes you have, it's going to take you log n time to hit just one node, which gives us the total number of chains you have in your path can be at most log n, and therefore the total time complexity that you have is order time required in a segment tree into the total number of chains you can have, which is log n the whole square per query. Tree construction requires us to do multiple depth first search, one for finding out the nodes in every subtree and the other one to break them into chains, and then also of course constructing the segment trees. That turns out to be order n plus the binary lifting, so that is n log n. So in order n log n time, you can decompose this graph using heavy light decomposition.
Now let's have a look at some code. Most of the main method is about initialization. The important method here is HLD, but let me just go over DFS so that it's slightly clearer. In DFS, we are setting the parent values of the 2 raised to power ith parent for every node. This is finding LCAs using binary lifting, and if you're not sure about this, have a look in the description below. The important method, of course, is HLD. Let's go there. What we have is a vertex and a parent, and we need to find the heavy light decomposition of this vertex. The HLD method is a little tricky to understand, so we'll try to understand step by step. The first thing to know is that it's very similar to a depth first search. Every time you visit a node, you're going to be visiting its adjacent nodes in the DFS manner. Secondly, for every node that we visit, we are trying to update some parameters relevant to that node. If you think about it, for every node, we need to find the chain that it belongs to, which will define the segment tree number that it belongs to. We need to know the position of that node in the corresponding segment tree. And one interesting thing that we do here is not create n number of segment trees. We don't create a segment tree for every new chain. Instead, we use the segment tree that we have built previously, and we just note down the position of this vertex in that given segment tree. That allows us to answer all the queries using a single segment tree instead of the number of segment trees being equal to the number of chains that we have in the HLD decomposition. After this, we find out the heaviest edge that we have. So you see that we are ignoring the parent. So this will give us the heaviest subtree for this node. If you have a child, then this variable will be set. You come here and you run the HLD on the heavy child with the vertex as its parent. Important thing to notice here is that the chain ID has not been updated. So the chain ID that you're sending to the heavy child is the same as the one you had right now. Another thing to notice is that in the array, which we are going to be using to construct the segment tree, we are actually passing in edge weights instead of the vertex value. Because each query or update that we are firing is going to be updating the edge weight, we just need to store this value here instead of this, the child vertex value. The base array being used for the segment tree is using a new position. So we just incremented position here. It's using the next position for this heavy edge. Finally, we come to all the light edges because we already used up the heavy child and we don't want to touch the parent. So for every light edge, we are going to be updating its chain ID. We are going to be stating that the chain head of this chain ID is the current vertex, update the base array, and do a heavy light decomposition on the new vertex. You can go over this code a couple of times. It's actually quite simple once you understand that it's a depth first search happening on every node where the heavy edges and the light edges are being treated differently. The final method we look at is called query up. It's used to answer queries on this tree. The update is actually extremely similar to how a segment tree update happens, so we'll skip that. You have the nodes U and V. What we do is we find the LCA of the two nodes U and V, and now we want to answer queries from U to the LCA and V to the LCA. Here the two nodes are mentioned as from and to. So this is the LCA and this is the node that we are querying from. So the current node is set to from over here, and we are going to be setting our initial answer as 0 because this is going to be the sum of the nodes from A to LCA. As you can see, as long as the chain is not equal to the chain that we have right now, so the current chain, which is starting from the base node, is not equal to the chain of the LCA, we are going to repeat this. What we have is the current chain head over here being used to query the segment tree from the current position to the current chain head. Now what is this going to do? This is going to make you run up to the start of the segment tree that we had. Alright, that's the line over here. And the second line is just setting the current node as the parent of the current chain head. This 0 means the 0th node. So that is basically 2 raised to the power 0, which is 1. Alright, so you can actually ignore this and just have a look at this bit, which is the current chain head's parent. With these two lines, what you're doing is running to the start of the segment tree in log n time and jumping to the next chain in order 1 time. You're going to do this till your chain matches the LCA chain, and finally, when that happens, when your chain matches the LCA chain, you can just do a single segment tree query from your current position to the position you're looking for and add that to the answer, after which you can return. That completes the code for heavy light decomposition.
If you have any doubts or suggestions on this, you can leave them in the comments below. If you liked the video, then make sure you hit the like button. And if you want notifications for further videos like this, hit the subscribe button. I'll see you next time.